So this video will start chapter 5. Chapter 5 is on chemical reactions. And so we will start with section 5.1, Introduction to Chemical Reactions. So let's have a reminder of what is a physical change versus a chemical change. So a physical change alters the physical state of a substance without changing its composition. So this means you do not change the identity of the substance when it goes through a physical change. It is still the same substance before and after. And typical physical changes are, for example, when you are changing from a solid state to a liquid state. For example, here you see ice in water, and so ice is a solid water, and you can see in the upper bubble here that molecules of water are packed together and arranged in an organized pattern. You see a pattern, it's an organized network. So this is representing a solid water. Now, if you let the water melt, you still have packed molecule, packed water molecules together, but instead of being arranged in a pattern, they are randomly put together. And so this is the liquid state showing in the bubble, the bottom bubble. And so when you go from ice to liquid water, you still have water at the end. It's just a change of physical state, a change of phase. So that's representing a physical change. Chemical changes, remember we said that they are equivalent to saying that you have a chemical reaction. So a chemical change is a chemical reaction, and it converts one substance into another. So this time you are changing the identity of the substances that you start with, and you will make new substances. So chemical reactions involve breaking bonds in the reactant. Reactant is the word that we use to designate starting materials. So the starting materials in this bubble here on the left are methane and oxygen. Methane is CH4 and oxygen, the molecule, is O2. And so if you make them go through a chemical change, a chemical reaction, so the arrow here symbolizes the chemical reaction. And you do that by having a spark, when you have a mixture of methane gas with oxygen gas, if you have a spark, it will ignite, and they will combust. The methane will burn, and you will obtain a product, which are different substances. And here you are producing carbon dioxide, CO2. So now the oxygen is bonded to the carbon, and the oxygen is bonded to the hydrogen, and with the molecule of water. So you form new bonds between oxygen and hydrogen, and between oxygen and carbon, bonds that didn't exist before. So you broke bonds in the reactant, and you form new bonds in the product, and that's how you make new substances. So that's what is a chemical reaction. It's a chemical change. So let's go through a quick learning check here, where you will decide if you have a chemical reaction or not. So please pause the video and do this on your own before you watch the answer. So photosynthesis, is this a chemical reaction or not? Photosynthesis, yes, it's a chemical reaction. In photosynthesis, what happens is that the carbon dioxide and the water combine to form carbohydrate, glucose, and oxygen. So it's a synthesis of carbohydrates from, you know, molecules you find readily, like carbon dioxide and water. Heating sugar until it turns black. So is this a chemical reaction? Yes, the sugar is decomposing. When sugar turns black, it's not sugar anymore. You know that sugar is white, a white crystal. And so if it's black, it's not sugar anymore. You've decomposed it into, it's like breaking it into gases, and then the black that you see is the carbon, some carbon left over. So sugar is decomposed, which means it's not the same molecule at the end, and so we have a chemical reaction there. Next, heating ice until it turns liquid. So this is not a chemical reaction, right? Because it's the example we saw earlier where the ice is melting, right? When you're heating ice, it's gonna melt and then change into liquid water, because ice is the name we give to solid water. So we have water to start with, and we finish with water. So it's a physical change, it's not a chemical change. Next, digestion of food. So this is also a chemical reaction. When you're digesting food, the food is decomposed. It's broken down into smaller pieces so that you can actually digest it. And you have some hydrochloric acid that is made in your stomach, and that helps decompose the food, break it down. So digestion of food is a chemical reaction. When you're dissolving sugar in water, is this a chemical reaction? No, even though sugar it looks like it disappears, you can retrieve sugar if you want to. When you're dissolving sugar in water, it just physically breaks the crystals into the molecules. And so the molecules now are surrounded by water molecules, and that's why you don't see it anymore, but it's there. If you tasted the water, it would taste sweet, so you would see a change. But it's a physical change, it's not a chemical reaction. If you are having this sweet water and you evaporate the water, you will retrieve the crystals of sugar. They will crystallize, and you will retrieve the solid sugar eventually. So it has not been changed into something else. Next, burning of alcohol in a flambé dessert. So you will have to learn that whenever you're burning something, this is a chemical reaction. Officially, the name is combustion. So combustion of alcohol in a flambé dessert. This is a combustion reaction, which is a chemical reaction. What happens when this combustion happens is that alcohol is combining with oxygen from the air, and it makes carbon dioxide and water. And so the alcohol is a liquid. It combines with oxygen that is in the air and that you don't see, and it becomes two gases, carbon dioxide and water. So that's why it looks like it disappears, but it's actually transformed into carbon dioxide and water, which are gases. So yes, this is a chemical reaction. Alcohol is broken down into two different substances. So you will learn to write chemical equations in this chapter. And so there are some symbols that we use. And so a chemical equation uses chemical formulas of the reactant and the product, and other symbols to represent the chemical reaction. And you have an example here of the actually the combustion reaction of methane with oxygen to form carbon dioxide and water. So by convention, we call the starting materials reactant, and we write them on the left. And we use an arrow to show there is a chemical change or a chemical reaction. And you write the formulas of the product on the right side of the arrow. The products are what are produced when the reactant react together. You see the formulas, and you are familiar now with chemical formulas. And then to the right of the chemical formula, you see letters in parentheses. These represent the physical state of your substances. So what the convention is, S represents a solid, L a liquid, G is a gas, and AQ are aqueous solutions. Aqueous solutions are a solution made of water. Water is the solvent. That's why it's called aqueous, because aqua means water in Latin. And so a solution made of water as the solvent is an aqueous solution. And so, for example, when you have sugar in water, this is an aqueous solution. And it can be a reactant or a product. The other symbol we see here in the table, the delta here symbolizes heat. Sometimes reactions occur only if you bring some energy, and this would be shown into the reaction above the arrow. You would have the symbol delta above the arrow to say that you need heat to have the reaction happen. So a chemical equation uses coefficients to show which proportion of reactants will react together and which quantity of product will be produced. So it gives you the proportions in which the reactant react. It's like a recipe. It's not necessarily one molecule of A will react with one molecule of B. It's more complex than that. You have to show the proportions, and coefficients are used for that. Coefficients are written in front of chemical formulas to show the number of molecules of a given element or compound. So in the example of the combustion of methane here, we have a coefficient 2 in front of the molecule of oxygen. And it says that one molecule of methane will react with 2 molecules of oxygen to make 1 molecule of carbon dioxide and 2 molecules of water. The 2 in front of water also means it's 2 molecules of water on the product side. So the coefficients are written in front of the formulas because you're not allowed to change the formulas. The formulas are set, you cannot change them. So that's why sometimes you will need to say more than one molecule of a given substance, and you will use coefficient for that. And so the law of conservation of mass states that atoms cannot be created or destroyed in a chemical reaction. And so we use coefficient to balance the equations, the chemical equations. When we have a balanced equation, it means it has the same number of atoms of each element on both sides of the equation. So when you have the same number of atoms on both sides of the equation, then the mass will be conserved. So that's why balancing satisfies the law of conservation of mass. And that's why we do balancing. It's to satisfy the law of conservation of mass. So let's go through an example here where we have methane plus 2 oxygen gives CO2 plus 2 H2O. So if we counted the number of atoms on the reactant side, so on the left side of the arrow, we have 1 carbon coming from CH4, 4 hydrogens coming from CH4, and 4 oxygen atoms. You do multiply the coefficient by the subscript for that atom, to get the total number of atoms on that side. So 2 times 2 is 4 oxygen atoms in this case, because each molecule of oxygen has 2 atoms of oxygen. And if you have 2 molecules, then it's 4 oxygen atoms in total. Then on the right side here, we have 1 carbon atom from CO2, 4 hydrogen atoms from 2 molecules of water, because each molecule of water has 2 hydrogens. And so you multiply the coefficient by the subscript, 2 times 2, and again we have 4 hydrogens on the right. And oxygen, so we have 2 oxygens from the molecule of CO2 and 2 other oxygens from the 2 molecules of water, right? The 2 here is multiplied by the coefficient 1 of oxygen in the molecule of water. It's implied 1. And so because you have 2 molecules of water and they each have 1 oxygen atom, then you have 2 oxygen atoms from those 2 molecules of water. Plus the 2 oxygens from carbon dioxide, that's 4 oxygen in total on the product side. So we see that we have the same number of atoms on the reactant side and on the product side. And so we can say that this equation here is balanced. It's balanced and it satisfies the law of conservation of mass, because we will have the same amount of mass on both sides, because we have the same number of each type of element present there. So let's practice counting the number of atoms on each side of the arrow. So state the number of atoms of each element on the reactant side and on the product side of the equations. So again, I would like you to pause the video and do this on your own before you watch the answer. So P4, phosphorus, plus 6 Br2 give 4 PBr3. And so if you count the number of phosphorus on the left side, you have 4 phosphorus, because there is no coefficient in front of P4. So it's like a 1. You have 1 molecule of P4, and 1 molecule of P4 has 4 P. So you have 4 phosphorus on the left. Then you want to count on the right. On the right, you have 4 molecules of PBr3, but each molecule of PBr3 has only 1 P. So that means you do 4 times 1, you know, the subscript 1 that is implied after the P. And that's 4 P on the right side. Let's count the bromine. On the left side, we have 6 molecules of Br2. So it's 6 molecules that contain 2 bromine each. So you do 6 times 2, and that's going to be 12 bromine on the left side. On the right side, you have 4 molecules of PBr3. And each molecule of PBr3 has 3 bromine. So you multiply 4 molecules times 3 bromine per molecule, and that's 3 times 4 is 12. So we have 12 bromine again on the right side. So we can say that this equation is balanced, because we have the same number of P's and Br on both sides. Let's look at the second equation here. We have 2 aluminiums in the solid state reacting with Fe2O3, solid as well, to give 2Fe, solid, plus Al2O3. So let's count the aluminum on the left side. We have 2 aluminums by themselves. So that means 2 aluminum on the left. On the right, we have also 2 aluminums, because we have 1 molecule of Al2O3, and that 1 molecule has 2 aluminum in it. So we have 2 aluminiums on the left and 2 aluminiums on the right. Let's count iron. Fe is the symbol for iron. Iron, there is 1 molecule of Fe2O3, and that molecule has 2 irons in it. So that means 2 irons on the left. And on the right, we have 2 irons because the symbol Fe is by itself, and there is a 2 in front. So it's 2 atoms of Fe on the right. Oxygen, on the left, we have 1 molecule of Fe2O3 that contains 3 oxygen. So that's going to be 1 times 3 oxygens on the left. On the right, same thing, but it's with Al2O3. We have 1 molecule that contains 3 oxygens, so it's going to be 3 oxygens on the right. So because we have the same number of aluminum, iron, and oxygen on both sides of the equation, this is also a balanced equation.